Welcome to the Deep Dive. We're here to take complex system stuff, architecture, and really break it down. Today, we're digging into something that sounds almost too simple. How do you count? Or maybe, more accurately, how do massive systems, think Twitter scale, generate billions of unique IDs? Without conflicts, super fast, and crucially, in a way that's actually useful later on.
It's a classic scaling problem, really. When you're just starting out, it's easy, right? You lean on your database, that auto-increment feature. It feels like a safety net. It's unique. It's ordered. Perfect.
Yeah.
Until you have more than one database server, that is.
Exactly. And that's where it falls apart spectacularly. The moment you need real scale, multiple servers, maybe just in data centers, that single counter becomes a huge bottleneck.
A massive bottleneck. You just can't have, say, 10 different servers all trying to grab the next number in the same sequence at the same time, trying to sync that up across a network. The latency alone would kill you. And if you don't coordinate, collisions. Guaranteed.
So yeah, generating unique IDs across many machines really fast, it forces you to fundamentally rethink what an ID even is.
Okay, let's get into this then. Our mission for this deep dive is to figure out what makes a good ID generator for these distributed systems. We're moving way past those simple database tricks. We're aiming for something robust, inspired by approaches like Twitter's Snowflake system.
Right. The goal isn't just uniqueness, that's table stakes. We need an ID that's engineered for performance, engineered for specific constraints. And we've got 5 key requirements straight from the source material. These are the constraints that basically break all the simple solutions right off the bat.
Let's list them out. First, uniqueness. Obvious, maybe, but it has to be globally unique. Everywhere, all the time, no exceptions.
Second, numerical. Just numbers. No letters, no dashes, none of that. Purely numeric.
Yep. Important for storage, indexing, sometimes compatibility too.
Third, and this one is a big deal, size constraint. It absolutely must fit within 64 bits.
This is huge. 64 bits sounds like a lot, but it's actually a very tight constraint when you think about database performance, especially indexing. It maps perfectly to that standard byte type.
Keeping it compact means faster lookups, better cache usage, performance, basically.
Exactly.
Fourth requirement, order. The IDs have to be sortable by time. Strictly increasing. Monotonically increasing is the term, right?
That's the one. An ID generated later must be numerically larger than one generated earlier, even if they came from different machines miles apart.
Crucial for database indexing again, and querying time ranges efficiently.
Absolutely critical.
And finally, number 5, scale. We need serious throughput. The system has to crank out over 10,000 unique IDs per second, system-wide, sustainably.
And that high volume, that's what really forces you away from anything centralized. No single point can handle that kind of load reliably.
Okay. 5 hurdles: unique, numerical, 64-bit, time-ordered, and high volume. So before we build the dream solution, let's really understand why the common approaches fail. Why don't they meet these 5 specific needs, especially that 64-bit limit and the time ordering?
Yeah, it's worth spending time here because pretty much everyone tries one of these first before hitting the wall. The distributed time and space problem is tricky.
Let's start with option A, multi-master replication. This feels like trying to keep that old auto-increment magic alive, just spread out.
It is, yeah. It's a clever trick on the surface. You still use auto-increment, but you tweak the step size. So if you have, say, K database servers, you set the increment step to K on each one.
Right. So if you have maybe 4 servers, K4, server 1 goes 1, 5, 9, server 2 goes 2, 6, 10, server 3 starts at 3, increments by 4, and so on.
Precisely. Each server gets its own non-overlapping set of numbers. It guarantees uniqueness across those specific 4 servers. Solves that basic problem.
Seems okay, but where does it fall down in the real world, operationally?
Well, first, it's brittle. Adding or removing servers is a pain. If you need to add a 5th server, you have to stop, reconfigure the step size and the starting offset on all the existing servers carefully without messing up. It's a recipe for downtime, or worse, collisions, if you get the reconfiguration wrong. Just really hard to manage flexibly.
Okay, that sounds fragile, but the sources really hammer on the order problem. How does it fail there?
Right. That's the killer flaw. Let's use your 4-server example. Server 1 is, say, in London, busy in the morning, issues ID 1001. Server 4 is in Tokyo, gets busy later in the day, issues ID 4.
So ID 4 was generated after ID 1001 in real time, but it's numerically much smaller.
Exactly. And think about what that does to your database index if the ID is the primary key.
Oh, that's bad. Inserting ID 4 after 1001 means the database has to jump way back in the index structure, potentially reading old pages off disk. It messes up the physical ordering.
Totally messes it up.
Yeah.
You get high index fragmentation, terrible cache locality. If you ever need to query show me everything since yesterday, relying on the ID for that, forget it. The order is completely broken across servers.
So multi-master is out for our requirements. What about option B, UUIDs? Universally unique identifiers. These seem like the go-to for avoiding coordination, right? Just generate them anywhere.
They are certainly tempting for that reason. A UUID is a 128-bit number. Each server just makes one up independently. And the 128-bit space is just mind-bogglingly huge, $200. The chances of two servers accidentally generating the same one are practically zero. Like the sources say, you could generate 1 billion UUIDs a second for a century and still have only a 50-50 chance of one collision. It's statistically unique.
Incredible uniqueness. So simple to generate. Why isn't this the answer then? This is where it gets interesting, right? Because it fails our specific constraints.
It fails hard on 3 of our 5 requirements. The biggest one. Size problem, 128 bits. That's double our non-negotiable 64-bit limit.
Okay, it's bigger. But why is double the size an operational disaster beyond just using more disk space?
Okay.
Is it really that bad?
It's not just disk space, it's about performance at scale, especially in memory and cache. Think about your database index. Index pages have a fixed size. If your key is 128 bits instead of 64, you can fit roughly half as many keys onto a single index page in memory. So when the database needs to scan the index, it has to read twice as many pages from memory, or worse, from disk. More I/O, more cache misses. It slows everything down. The difference between a compact 64-bit integer index and a sprawling 128-bit index can be massive underload. It's all about that efficiency.
Right, index density. Fewer keys per page means more page fetches. That makes total sense. We're optimizing for speed here.
Exactly. Then there's the format problem. Most common UUIDs, like V4, are random bits often shown as hex strings with dashes, like 09C93, 62, something something. That violates our numerical-only rule. It can complicate storage, queries, and interfacing with systems that expect plain numbers.
And the third failure.
The order problem, again. Standard random UUIDs, like V4, have absolutely no time ordering. They are completely random. Even the time-based versions, like UUID V1, don't give you the strict, monotonically increasing order across machines that we need for efficient indexing. You end up with the same fragmented, slow index problem as multi-master.
So UUIDs are great for pure, uncoordinated uniqueness, but terrible if you need compact storage, numerical format, or time-based sorting for performance.
Precisely. They solve one problem, but create others that are unacceptable for our specific use case.
Okay, 2 down. Let's look at option C, ticket servers. Flick used this, right?
Yeah.
Trying to bring back centralization, but manageably.
Yeah, the ticket server idea is clever. You dedicate one, maybe a couple of highly reliable database servers just for auto-increment. That's their only job. Your application servers don't generate IDs directly. Instead, they ask the ticket server for a block of IDs. Say, give me the next 4,000 IDs. The app server caches those 1,000 IDs locally and hands them out as needed. When it runs low, it asks for another block.
Okay, I see the appeal. You get numerical IDs. They should be sortable, mostly. And because you fetch big blocks, you're not hitting the central server constantly. Reduces the network chatter.
Right. It's easier to implement initially, especially for systems that aren't at massive scale yet. It keeps that nice sequential property.
But there's always a but. What's the catch here?
The classic single point of failure, or SPOF, if that one central ticket server goes down.
Everything stops. No new IDs can be generated anywhere until it's back up. Every part of your application that needs to create something new is blocked.
Exactly. It's a critical dependency.
So the obvious fix is add a second ticket server for high availability.
But now you've walked right back into the coordination problem.
Right. If you have 2 ticket servers, how do you make sure they don't accidentally give out the same block of IDs? Server A gives out 1001, 2000. Server B needs to start at 2001.
Exactly. You need some other system, a distributed lock manager, a consensus protocol like Paxos or Raft, something external to make sure those ticket servers coordinate their number ranges perfectly.
So we haven't actually solved the distributed coordination problem. We've just moved it. We pushed the complexity into managing the ticket servers themselves.
Correct. And even the sortability isn't perfect. If server A gets block 1001, 2000, uses some, then crashes. Server B might later get block 501, 6000. You have gaps, which is okay, but ensuring strict time order across servers issuing potentially large cached blocks gets complicated again.
Okay, fascinating. So, to recap, multi-master, fails on ordering and management. UUIDs, too big, wrong format, random order, ticket servers. Become a SPOF, or reintroduce coordination complexity when you try to make them reliable.
Which leads us to the conclusion that none of these off-the-shelf or slightly modified database tricks work when you have all 5 of our requirements: unique, numerical, 64-bit, time-ordered, and high volume. We need something designed from the ground up, where the ID structure itself enforces these properties.
Right, so we need to engineer the ID itself, using that fixed 64-bit space, not as a limitation, but as a canvas. This is where the Snowflake-inspired approach comes in. Divide and conquer on the bits.
Exactly. The core idea is brilliantly simple, actually. You take those 64 bits and you divide them into dedicated sections. Each section has a specific job: telling time, identifying the source, handling concurrency. By packing this metadata into the ID, you guarantee the properties by construction rather than relying on external coordination.
Okay, let's break down that 64-bit structure. What are the pieces?
So first, bit 63, the most significant bit. That's the sign bit, just 1 bit.
And it's always set to 0, right? Basically reserved, keeps the number positive, plays nice with systems that assume signed integers.
Correct. Just ensures it's always treated as a positive number. Then, the most important chunk for ordering, the timestamp. This gets a big slice, 41 bits.
41 bits for time. That's the heart of the sortability.
Absolutely. Next, we need to know where the ID came from. So we have 2 parts for location. Data center ID gets 5 bits, and machine ID also gets 5 bits.
5 bits each, okay. So that pinpoints the specific generator node.
Yep. And finally, to handle lots of requests coming in at the exact same time on the same machine, we have the sequence number. That gets the remaining 12 bits.
Let's add that up. 1 sign plus 41 timestamp plus 5 data center plus 5 machine plus 12 sequence. That's 64 bits. Exactly.
It fits perfectly. So structurally, we've hit the size and numerical constraints. Now, how do these pieces work together to give us uniqueness, order, and scale?
Let's start with the location bits, data center, and machine IDs. 5 bits each seems specific. Why that number?
It's a trade-off, like everything in this design. You only have so many bits to spend after allocating for the timestamp and sequence. 5 plus 5 is 10 bits for location was deemed sufficient for the kind of scale expected.
And what does 5 bits give you, capacity-wise?
Well, 2 every 5 buys is $32. So 5 bits for the data center ID allows for 32 distinct data centers or logical regions, and 5 bits for the machine ID allows for $25 equals 32 unique machines within each of those data centers.
So total capacity is 32 data centers times 32 machines per data center.
Yeah.
That's 124 unique generator nodes globally.
Yeah, 124 nodes, that's pretty substantial capacity built right into the ID structure.
And this combination is key to uniqueness, right? Even if 2 machines in different data centers or just different racks generate an ID at the exact same millisecond with the same sequence number.
Their data center plus machine ID bits will be different. So the final 64-bit ID will be unique. It provides that global uniqueness guarantee.
Okay, but operationally, how do you assign these IDs? You can't just let machines pick random ones, can you?
No, absolutely not. This requires careful provisioning. When a new ID generator server starts up, it needs to be explicitly configured with its unique data center ID and machine ID. These are fixed values for the life of that process or instance. You need some kind of central registry or configuration system to manage this pool of 10 and 24 possible node IDs and make sure you don't accidentally assign the same combination twice to running servers.
What happens if someone makes a mistake? They deploy a new server and accidentally give it the same data center machine ID pair as an existing running server.
Instant potential for collisions. If those 2 machines happen to generate an ID in the same millisecond and hit the same sequence number, they will produce the exact same 64-bit ID. That's a critical failure. So the sources emphasize this. Managing these node IDs requires real operational discipline. Configuration reviews, automation, checks. It's where the human element meets the system design.
Makes sense.
Yeah.
Okay, let's move to the biggest piece, the timestamp. 41 bits. How does this guarantee the ordering?
It's pretty straightforward. The 41 bits store the number of milliseconds that have elapsed since a specific fixed point in time, the epoch. Since this 41-bit chunk occupies the most significant part of the ID, after the sign bit, a timestamp from a later millisecond will always result in a larger number in this section, which means the overall 64-bit ID will be numerically larger. Boom. Monotonically increasing, globally sortable by time.
Now, about that epoch, it's not the standard Unix epoch. Janverd 1970, is it? Twitter Snowflake used a custom one, November 4, 2010. Why add that complexity? Why not just use the standard?
It's all about maximizing the lifespan within those 41 bits. Remember, 41 bits isn't infinite. It can hold 200 milliseconds. If we started counting from 1970, a large chunk of that capacity would already be used up by the time the system was deployed in, say, 2010.
Ah, I see. So by picking a custom epoch closer to the system's launch date, like November 4, 2010, you effectively reset the counter. You get the full range of those 41 bits for the system's future operation.
Exactly. It buys you time. And how much time? Well, 2 milliseconds is roughly 69 years.
69 years. So starting from the 2010 epoch, the system is designed to work correctly until around 2079.
That's the theoretical limit based on the timestamp bits. After 69 years, that 41-bit counter will overflow.
Planning for a problem 69 years away, that's some serious forward thinking. It gives the system a very long, predictable lifespan.
It's a conscious trade-off. Add a little complexity, the custom epoch, to gain a lot of longevity. It really shows how you tailor the bit allocation to the expected service life.
Okay, last piece of the puzzle, the sequence number. 12 bits at the end. This handles the high throughput requirement, right? The scale.
Yes, this is the key to handling bursts of requests within the same millisecond on the same machine. 12 bits gives you 212 dominations.
Which is 4U96.
Right, 4U96 unique values, 0 through 4U95. For every single idea generated on one specific machine within the same millisecond, this counter just increments by 1.
So, if 50 requests hit the same generator node in the very same millisecond, they all get the same timestamp, same data center machine IDs, but the sequence number goes 0, 1, 2, up to 49. That keeps them unique.
Exactly. That's the uniqueness guarantee at the micro level. But the scale comes from how quickly it resets. The sequence number resets back to 0 every single time the millisecond clock ticks over.
Ah, so you get a fresh batch of 4096 possible IDs every millisecond. It's like a counter that refills constantly.
Precisely. So theoretically, what's the maximum throughput per machine?
4096 IDs per millisecond. Multiply by 1,000. That's 4.096 million IDs per second per machine, theoretically.
Which utterly dwarfs our requirement of 10,000 IDs per second system-wide. Even one machine has vastly more capacity than needed thanks to those 12 sequence bits and the millisecond reset.
Okay, but what happens if you actually do exceed that? What if one machine gets hit with, say, 5,000 requests in a single millisecond? The counter only goes up to 4095.
Good question. The generator must handle this gracefully to prevent wrapping around and creating duplicates within that millisecond. When the sequence number hits its max value, 4095, the generator has to effectively pause. It must wait until the system clock ticks over to the next millisecond. Only then can it reset the sequence number to 0 and start serving requests for that new millisecond timestamp.
So it intentionally introduces a tiny bit of latency in that extreme burst scenario, rather than generating a duplicate ID.
Exactly. It blocks briefly, ensuring uniqueness and maintaining the time order. That's the safety mechanism.
Okay, so we've designed this ID. It meets the 5 criteria on paper, but running this in the real world. Distributed systems always have hidden gotchas. What are the operational challenges?
The absolute biggest one, the Achilles heel, if not managed properly, is clock synchronization. The entire design hinges on the assumption that time is consistent and moves forward steadily across all your generator nodes. The timestamp segment, the millisecond reset of the sequence number, it all assumes accurate clocks.
And server clocks? Well, they drift. They're not perfect atomic clocks.
None at all. You have 2 main problems. First, clock skew or drift. One server's clock might gradually run slightly faster or slower than another's. If 2 machines have drifted significantly, they might generate IDs for the same wall clock time but end up with different timestamp values. Or worse, if they drift together, they might conflict.
Okay, drift is bad. But what about clocks suddenly jumping, especially backward?
That's the really dangerous one. Clock steps, especially backward steps. This can happen if you're using something like Network Time Protocol, NTP, to keep clock synced. If NTP realizes the server's clock is way too far ahead, it might forcefully set it backward.
And if the clock goes backward?
Disaster. The generator could issue an ID with timestamp T, then the clock jumps back. Then it issues another ID, but with timestamp T minus something. You've immediately violated the sortable by time requirement. And even worse, if it jumps back to a millisecond it already processed, it might reuse a timestamp and a sequence number, creating an exact duplicate ID collision.
Yikes. So how do robust Snowflake implementations prevent that backward clock jump from causing chaos?
They have to be defensive. A common strategy is for the generator process to remember the timestamp of the last idea generated. Before generating a new ID, it checks the current system time. If the current time is less than the last timestamp it used, meaning the clock went backward, it must refuse to generate an ID using the current time. It might throw an error Or more likely, it will simply block and wait until the system clock catches up to and surpasses the last timestamp it successfully used.
So again, it introduces potential latency as a safety measure against time going backward.
Exactly. It prioritizes correctness, uniqueness, and order over lowest possible latency in that edge case, which means
Absolutely need a reliable time synchronization mechanism, like NTT, running well on all of the generator machines. The ID system's correctness depends heavily on the underlying clock sync.
it's a critical dependency. The system is only as solid as its time source.
Okay, clock sync is key. What else? You mentioned the bit allocation 415512 isn't necessarily fixed. Section length tuning.
Right. That specific layout is just one possibility, optimized for a balance of longevity and high concurrency. But you can absolutely tune it based on your specific application's needs.
So let's say you have an application that doesn't need massive concurrency, maybe only peaks at a few hundred IDs per second globally, but it needs to last for a very long time, like maybe 100+ years.
Perfect scenario for tuning. You don't need 12 bits, 4096 IDMs, for the sequence number if your peak is only a few hundred per second. You could perhaps shrink the sequence number down to, say, 8 bits. 208 ABUTs is 256 IDs per millisecond per machine. Still way more than enough for your needs.
Okay, so reducing the sequence from 12 bits to 8 saves us 4 bits. Where do those bits go?
You reallocate them, you add those 4 saved bits to the timestamp section. So instead of 41 bits for the timestamp, you now have 41 plus 4 equals 45 bits.
And what does adding 4 bits to the timestamp do to that 69-year lifespan?
It extends it dramatically. Each extra bit doubles the range. So 4 extra bits means 24 equals 16 6 times longer. Your 69-year limit potentially jumps to over 1,000 years. You sacrifice unneeded concurrency capacity to gain significantly more longevity. It's a direct trade-off, all within that fixed 64-bit total. You tune it for your specific requirements.
That's really flexible. It shows the power of designing the ID structure itself. And finally, just to state the obvious, for any critical system like this, high availability.
Absolutely essential. We've designed the ID structure, but the service that generates these IDs needs to be highly available. This generator's fundamental. If it's down, write stop. So you'd never run just one instance. You run a cluster of generator nodes, probably behind a load balancer. If one node fails, hardware issue, network glitch, whatever, the others seamlessly take over. The system needs redundancy baked in, using those unique data center machine IDs to ensure continued operation without collision.
Right. The design allows for distribution, but you still need standard HA practices to make the service reliable. Okay, let's wrap this up. We went on quite a journey. Started with simple auto increment, saw why it fails at scale, looked at UIDs, saw they were too big and broke indexing, considered ticket servers, found the SBOF or coordination problems, and we landed on this engineered 64-bit Snowflake-style ID. Sections for time, location, sequence. It's a really neat example of optimizing within tight constraints, isn't it? The 64-bit limit forces this kind of clever design.
It really is. The complexity isn't just generating a unique number, it's generating one that meets all these other requirements simultaneously: size, order, scale, especially under the weirdness of distributed time. And it leaves us with a final thought, something for you, the listener, to consider. We talked a lot about generation and the 69-year lifespan based on that 41-bit timestamp in the 2010 epoch. That overflow point is way out there, around 2079. But what happens in, say, 2078 or even 2070 when that timestamp field is getting close to full? Eventually, it will wrap around. It will hit all ones and then roll over to 0. If it rolls over, it will start generating timestamps that look like they came from 2010 again, potentially colliding with the very first IDs ever generated by the system decades earlier. How do you plan for that? You have a hard deadline, decades away, where your primary key generation mechanism fundamentally breaks. Do you migrate to a new epoch, start using the sign bit, maybe move to 128-bit IDs after all? It's a massive migration challenge involving potentially trillions of records, all stemming from that initial 41-bit design choice made 70 years prior. Planning for that kind of future maintenance decades in advance. That's the truly long-term challenge in systems design, something to think about.